Hello and welcome back to another quick update on Switch Connect program. I am Anant Alwar, Technical Marketing Engineer with Aruba CX Switching TME team. And today in this session, we are going to discuss certain properties and techniques associated with your transceiver modules. So let's get started. So as I was mentioning, the first we will going to talk about the modulation techniques. So modulation is basically the process of encoding the digital data that we are getting from our devices onto an analog carrier signal for transmission over a communication channel. In context to a switch transceivers, when data is coming from your switches, it cannot be readily transmitted via your network cables. That's where the modulation comes in, where you convert your digital signals generated by your switch onto an optical signals which is suitable for transmission over fiber optic cables. Now we currently broadly have two types of modulations in our transceivers. First one is NRZ and the other one is PAM4. Both of them are very much different on the various factors, and let's discuss each of them briefly. The first one is about the encoding method. So for NRZ, we only have two voltage levels for this modulation. That's 0 and 1. On the other hand side, for PAM4, we have four voltage levels for this modulation. That is 0, 1, 2, and 3. So the data rate offered by NRZ is lower than what you see in PAM4 modulation because you are along only two voltage levels. That means only binary encoding can be done. On the other hand, for PAM4, it supports higher data rates by encoding two bits in a single symbol so that you get double the data rate. Bit rate is all about, let's consider it the same baud rate and on the same symbol. In case of NRZ, you are able to transmit only one bit of data. While on the other hand, for the case of PAM4, for one symbol, you are actually representing two bits of data. And hence, when you look at it broadly, PAM4 is actually doubling your data rate, which you can transfer over your transmission media. Because of this higher data rate offered by PAM4, you will find most of the time that PAM4 is being offered in our high end or high range transceivers, which are SFP56, QSFP28, or QSFP-DD, subjected to 40 gig, 100 gig, or 400 gig transceivers. For the other ones, for the lower speed variants, such as SFP, SFP plus, SFP28, QSFP plus, and QSFP28, we typically see NRZ type of modulation. Let's now talk about the optical parameters that are associated with your transceiver modules. So before coming to the exact topic, I just want to mention that each optical transceiver is designed to cope up with the loss of power inside an optical fiber cable, which means that when you are transferring your data through a transmission medium, which in this case is fiber cable, it is supposed to lose certain power inside it. And that's how our transceiver modules are designed to cope up that loss. In transceiver guide, you might have seen these details included for every transceiver module with a section naming optical parameters. And again, it will mention two basic properties that are transmit power and receive power with certain values. Now, what does it mean for your interconnect and how does you can get benefited from these values and what you can understand from it? First is the link loss tolerance. So what does link loss tolerance means? Think of it this way that when you are transferring your data from one point to another, as I mentioned, since the link is supposed to face certain amount of loss and a power is loose in this transmission media. So after even that loss, when it reaches to the other end, it is within the threshold of these receive powers. So link loss tolerance gives you the maximum allowable channel loss that you can go through while transmitting your data from one point to another. Numerically, it is calculated as the minimum, it is as the difference between minimum transmit and receive power levels. Here I took an example of our 40 gig ER4 transceiver with receiving power in this range and transmitting power in this range. Now, to calculate your allowable link loss, you just have to subtract your minimum transmit power from your minimum receive power, and you'll get this value. So what this value means? So when you are creating a link, and if your link faces the loss anywhere between 0 to 218.5 decibels, your link will operate without any issues. Anything beyond 18.5 decibels, you might want to consider certain other factors as well, because then your transmission will not be fulfilled because data is lost before it reaches to your receiver's end. The next is attenuation. So what does attenuation actually tell you? Now, when you are transferring data through a fiber optic cable, your light will attenuate its power as it moves through that fiber optic cable. Now think of a case when you transferred your light from your transmitting end, and when it reaches to the other end, it crosses the value, the threshold of that maximum receive sensitivity. In that case, it might damage your transceiver module. So you might want to know that how much attenuation is required between in this link, so that when you receive that power on the other end, it is within that certain range of receive sensitivity. That's why you calculate attenuation as the difference between maximum transmit power. So you're transferring your data with maximum transmit power, and even though when you transmit it with the maximum transmit power, if it is reached to the receiver's end under the maximum receive sensitivity, the attenuation is coped up with, or that is the actual attenuation that will work for your link. So that's why you need to calculate this attenuation as the difference between maximum value of transmit and receive power levels. Here I have taken the example once again for ER4. You can see the maximum values of transmit and receive powers are -4.5 and 4.5. So the required attenuation for your link is around 9 decibels. So what is the use case of this value? So when you are using a fiber cable with less light loss than expected, in order to achieve this required attenuation for lower distance values, you might want to use a attenuator. And for that purpose, you might want to know what is the exact attenuation you might require. That's what you can calculate using this value. So the violation, as I was mentioning earlier, if you violate the above criteria, it may lead to overdriving your receivers and resulting in either a non-operational link or in some cases permanently damaging your transceiver. So with this, I'll stop right here for this session and I'll see you in the next session. Thanks a lot for watching this video.